Molecular shape and polarity. In order for a molecule to be polar, it must have polar bonds, and we already talked about how to figure out whether a bond is polar or not due to the electronegativity difference. And then if it's unsymmetrical. So you could actually have a molecule that has polar bonds, but if it's symmetrical, it could be nonpolar altogether. And we'll talk about that a little bit more specifically in this section. So molecular polarity, looking at a really, really simple example of hydrochloric acid. Now on the periodic table, you know that hydrogen's all the way to the left and chlorine is all the way to the right, and they have a huge electronegativity difference. So big and obvious that you don't even really need to calculate it. So we know that that bond is polar. The bonding electrons are pulled towards the chlorine since chlorine is more electronegative. That makes chlorine a partial negative charge and hydrogen a partial positive. We usually draw these dipole moments showing the arrows pointing towards chlorine with a little positive side towards the hydrogen showing the hydrogen's more positive, chlorine's more negative because it's pulling the electron towards itself, making a polar bond. Now, if we show this in terms of electrodensity, note how this region for where the chlorine is a lot more yellow and a lot bigger. That's because the electron density is a lot higher since it's pulling more of the electron density to itself compared to hydrogen having a lower electron density. Now, that was just one bond because it was a diatomic molecule. What if we have more of a polyatomic molecule? If we look at carbon dioxide, the carbon and oxygen bond are actually polar. The molecule as a whole is linear. The bonding electrons are pulled equally towards both oxygen ends of the molecule in opposite directions. There is no lone pairs on the carbon to offset any symmetry. This is a completely symmetric molecule. I know oxygen is more electronegative than carbon, so both oxygen pull the electron more towards themselves. Now they're going in opposite directions. The dipole moment of one exactly opposes the dipole moment of the other. This causes the two dipole moments to sum up to zero, making the overall molecule nonpolar. Because they're spreading in opposite directions, they're opposite of one another and sum to zero. Dipole moments can cancel each other because they are vector quantities. So the way that we are going to look at figuring out the polarity of a molecule is through envisioning dipoles as vectors. They have both a magnitude and they have a direction. So they can have a number, and because they point a different way, they have a direction. So we think of them as vectors. Think of each polar bond as a vector pointing in the direction of the more electronegative element. So when we draw a dipole now, we're thinking of a vector going towards the more electronegative element. The length of the vectors is proportional to the electronegativity difference between the bonding atoms. Now that electronegativity difference is something you can calculate from that chart of the electronegative numbers, figuring out, 3.5 minus 2.1, that would be the distance of the vector. In carbon dioxide, there are two identical vectors pointing in the opposite directions. The vector sums to zero. Much like if we said this was positive 1 and this was negative 1, the total is 0. Therefore, the molecule is nonpolar. The hydrogen-oxygen bond in water is polar and the shape is bent. Now, the difference here, because of the asymmetry of the molecule, actually makes the whole molecule polar, not nonpolar. Each bond acts as a vector, and this time they're pointing towards the oxygen. So they're pointing the same exact direction. So instead of canceling out, they sum up to an overall net dipole going up towards the oxygen. This set of bonding electrons are pulled to the oxygen end, which makes the oxygen end a lot more electron dense and therefore makes the entire molecule polar. Looking at another structure, here we have ammonia. Now, nitrogen and hydrogen bonds are all polar. Here, my little vectors are drawn towards the nitrogen. Since the nitrogen is more electronegative, it pulls the electron towards the nitrogen. This is a tetrahedral shape. It has its lone pair of electrons up here, so it offsets the symmetry and pulls the electron up for a net dipole going towards the nitrogen, therefore making a polar molecule. Talking a little bit more about vector addition. To add two vectors that lie on the same line, assign one direction as positive and one as negative. So you're thinking of planar molecules when you think of the same line, right? They're exactly on the same angle. Vectors pointing in that direction have positive magnitudes. So here in example 1, do you see how both of these vectors go in the same direction and we give them a positive magnitude of the same number, so they would sum up together to go one big direction. In the second example here, we have a vector pointing one way and then a vector pointing another way. However, because the electronegativity difference is larger to the right, when they sum together, it will be polar towards the right side. Vectors pointing in the opposite directions have negative magnitudes. Now again, the numbers come from the electronegativity difference. If they're exactly the same, they cancel out and they have a net result of 0, and therefore non-polar molecules. To add two vectors, draw a parallelogram in which the two vectors form two adjacent sides. So here you have one vector and then you have another vector, and we draw a parallelogram by just drawing a line and another line to kind of connect them, where the sum of the two would be right in the middle. Draw the other two sides of the parallelogram parallel to the same length as the two original vectors. Draw the resultant vector beginning at the origin and extending to the far corner of the parallelogram. So these are just two examples. We have one vector going this way, so that's where my electronegativity is pointing. Then it's pointing like this. So to connect the dots, I would draw a line here, and my sum would be right in the middle to the end corner. To add three or more vectors, add two of them together first, and then add the third vector to the results. So again, we have the A and the B just like before, right? And then they sum up to this R. And then when I have C that's pointing down, that then gets added to the R, to the give me. So I have my R here and then my C. These sum together to give the middle region right here of my R prime. For another example, I have my one vector and my other that sum up to my top new vector here that then sums to my bottom, which then, because they have the same magnitude, would actually equal 0. So that's kind of tricky to know, but we have kind of a generic spread of what type of molecular shapes are symmetric and which are asymmetric to tell you which one would be polar or nonpolar. We determine whether a molecule is polar or nonpolar by summing the vectors associated with the dipole moments of all polar bonds together. If the vector sums are 0, nonpolar. If they have a net vector pointing in a direction, then it's polar. A linear molecule, a trigonal planar molecule, and a tetrahedral molecule are symmetric in all angles. Therefore, cancel out most of the time and would have a nonpolar arrangement. A bent or trigonal pyramidal, due to the electron from the lone pairs offsetting the symmetry, would result in a polar molecule. Let's practice that. Determine whether each molecule is polar or nonpolar. So let's start with drawing the Lewis structure for ammonia and figuring out the shape. This is trigonal pyramidal. So I know, without even knowing the shape, this offsets my symmetry, and my nitrogen is more electronegative than my hydrogen. So my vectors are all pointing inwards. So they all have a positive magnitude and would sum up to an even larger vector, making this polar. Carbon tetrafluoride. Carbon, fluorine, 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 and fluorine. Now, my fluorine is more electronegative than my carbon, so my vectors are all pointing outwards. Because this is a tetrahedral shape, they all have a 109.5 degree angle, and they're all symmetrically pulling outward in opposite direction, canceling each other out. These two would sum this way to be a net of 0, and these two would be a net of 0, non-polar. Last little bit of practice. Now, this is another engagement question. I want you to take a moment and explain why carbon dioxide and carbon tetrachloride are both nonpolar, even though they have polar bonds. So I want you to take a sentence or two or draw diagrams to explain this to me. Determine whether each molecule is polar or nonpolar. So let's start by the Lewis structure. This is a bend shape. My chlorine is more electronegative than my sulfur. This is a bend shape, so without even looking at where the electronegatives are pulling, I know that this is polar based off of its shape. Now I have sulfur, chlorine, chlorine, and chlorine. Actually, I was wrong here. Sulfur is more electronegative than chlorine. So, in my other structure, now we have a tetrahedral shape. So usually, actually, do we have a tetrahedral shape? 4 times 7, 28, plus 6, 32. 2, 4, 6, 8, 32. What am I missing? Well, since sulfur is more electronegative than my chlorine, they all point towards the sulfur going in the same direction, therefore making a polar molecule. Lastly, I have my bromine pentachloride. Now, chlorine is more electronegative than bromide. It's further down on the periodic table. And what shape is this? This is a square planar shape. 1, 2, 3, 4, 5. One, 2, 3, 4, 5. This is not square planar. This is seesaw. Because of the 90-degree and the 120-degree angles being equidistant from one another, this is a nonpolar molecule. So it can get a little tricky, but the important thing is to know is where is it pointing, and then if you have lone pairs, does it make the angle symmetric or asymmetric? Would that cause your molecule to be polar or nonpolar? So remember, I want you to answer this question as an engagement problem for this lecture today, along with the other ones from the previous videos.